Hey guys, I had a request earlier that I do some problems, just some of the examples for mole conversions. I know that can be a little bit tricky sometimes, and especially when you're not in the classroom learning it, that can just be pretty tough. So something that I like to show, and I try to show this in the notes. If you guys went to the notes sections of Teams, you would have seen where I kind of try to teach this and almost freehand writing notes with it, which was kind of tough. But I wanted to show this. This is just kind of a chart that I like to use that sets everything equal to each other. Now, one thing I wrote in those notes was trying to get you guys to understand that when I use the term a mole is just a number, just like a dozen is 12. A mole is just a number, it represents a number, except it's a bigger number than 12. Like if I said, I wouldn't walk in a donut shop like I use an example and say, hey, I want 48 donuts, I'd say I want 4 dozen donuts. But we're not going to go in when we're talking about atoms and say, oh, I need, you know, 12.04 times 10 to the 23rd atoms, we're going to say, hey, I need 2 moles of atoms. So we just group things together. That's how we count things really big. So that's really what a mole is. So when I look at this, I can say 1 mole equals 6.02 times 10 to the 23rd particles, or molecules, or atoms. Those are usually the units right there. Now, the other thing that we can look at is we look at the weight. Where this number actually came from was they took a periodic table and they said, okay, well, carbon has a mass of 12, and they actually looked at the mass of carbon having 12 protons and 12 neutrons, and they used that. And they said, okay, well, carbon has a mass of 12 protons, or not 12 protons, 6 protons and 6 neutrons, so it'd be a mass of 12 total. So they said, okay, well, if carbon has a mass of 12, how many particles of carbon would that be on average? And they figured out, well, wait a second, in order to get a molar mass of carbon being 12.011, you would need 6.02 times 10 to the 23rd atoms, carbon atoms. Then they looked at that for other atoms, said like magnesium. Magnesium has a mass of 24.305. So they said, okay, well, how many magnesium atoms, if you just grab all these magnesium atoms, how many would it be to get that mass, 24.05? And it was 6.02 times 10 to the 23rd. It just kind of works out that way. There's a reason behind it, but it just works out. So really what we can say is that the molar mass, which is the mass on the periodic table, contains this many atoms. So if a mole contains this many atoms and the molar mass contains that many atoms, that means this happens to be equal to the mole as well. So the mass is equal to 1 mole. Because if this is a mole, then this is going to be equal to this mole, or this mole. It's the same thing. It's like saying 1 dozen eggs has a mass of this. Well, 12 eggs has a mass of this. It's the same thing because 1 dozen is 12, so they have the same mass. And that's really what we're getting with that. Now, I like to use this because now we can write these out as conversion factors. So I can say 1 mole equals this, 1 mole equals this, or 6.02 times 10 to the 23rd particles equals this. So we can just use that. So I always have this up. If we were doing this in class, I would have this up for the entire unit because we'd just be talking about it all the time. So I like this little triangle. It really helps me out. So to use it, now I came up with a couple of problems. Wrote them out so I can go a little bit faster through this. So the first thing I wanted to do is I wanted to just make a conversion using this little like triangle, but a couple of different ways, a couple of different problems. So in the first problem, I'm going to go from grams to moles. The second problem, I'm going to go from molecules to grams. And then the third problem, I'm going to go from moles to grams. So just so you can see where I can go this way or this way or this way, really you can go any way around here, and you can just use this for conversion factors. So the first problem I did was converting 13.7 grams, and I came up with a compound. In this case, I said potassium carbonate. So potassium carbonate, you have to be able to write the formula correctly. If you don't write the formula correctly for that, you're going to get the problem wrong. So you have to be careful about that. So potassium carbonate. So when I write potassium carbonate, I have to figure out, okay, potassium is K and it's 1 positive. I get that because on the periodic table, it's 1 positive. And then carbonate on the backside, if I look on the backside of my periodic table, I find carbonate, and carbonate is CO3 2 negative. So I know that this is CO3, that's 2 negative. So that means if that's a 2 negative and a 1 positive, I need 2 potassium. So if I write the formula correctly, it's going to be K2CO3. And then I'm going to draw my chart. And in this case, I'm going from grams, and I'm going to go from grams to moles. So if I want to go from grams to moles, I need to look, okay, well, grams needs to cancel out. So I need grams down here. So in order to get grams down there, I need the molar mass. So to get moles up here, I'm just going to get grams on the bottom, moles on top. So I'm going to write on top 1 mole. I should have started a little bit down. I'm going to lose my room right now. K2CO3. That's okay. It looks like I'm okay. And now I need to find the molar mass. So the molar mass, I'm just going to figure it out from this formula. So I'm going to write molar mass from potassium carbonate. I have to add that up. Okay, so I'm going to do this. So potassium, I have 2 potassiums. If I look on my periodic table, potassium right over here has a mass of 39.1. So I'm going to write that down. It's 2 times 39.1. So 39.1, and then 39.1 times 2. You just calculate that out real quick, and you can say 39. Oh, batteries. Oh no. Okay, 39.1 times 2, and that's going to be 78.2. Then I'm going to do the same thing for carbon. Carbon, but I only have one of those, 12.0. Of course, that's going to equal 12.0. And then I have oxygen, where I have 3 of them. So 16 times 3, 48.0. If I add all those up together, I'm going to end up with a mass for potassium carbonate to be 138.2. Well, that's my molar mass for potassium carbonate. Again, 2 potassiums at 39.1 each gives me a mass of potassium of 78.2. I have only 1 carbon in here, so that's 12 grams, but I have 3 oxygens at 16 grams each. That's 48. You add those up together, and I end up with 138.2. So I'm going to put 138.2 right here. My units cancel. Again, this is just like what we did in Unit 1 when we just did our factor label. So units cancel, good to go. I just run my calculation. This one comes out to 0.0991. And my units are moles. It's funny because mole is spelled M-O-L-E, but for whatever reason they decided they wanted to abbreviate it, and its official abbreviation is M-O-L. So they just dropped the E. So that's why if you notice in my notes or wherever, I just have a habit of not writing the E because I never do. Just been doing that for years. So I just forget about it and don't even think about it. So mole does have an abbreviation of M-O-L. I don't know why they did that. They just did. Okay, so that's 0.0991 moles, 3 significant figures. We got 3 significant figures there. This doesn't count because that's an exact. And then I just write out what it's of. 0.0991 moles of K2CO3. And that would be my answer. And that's it. So I had another example. Said I was going to do 3 of them. So that's my first one. Again, using this triangle really helps me out. You have to make sure you have your formulas written correctly and calculate your molar mass correctly. If you write this formula wrong, this mass is going to be wrong. Because if you said KCO3, which would be pretty common, you would end up with the wrong number right here, which give you the wrong number here, give you the wrong number there, result in the wrong answer. Got to be careful about that. Okay, next one. I wanted to go from molecules to grams this time. So it's a little bit different because this was grams to moles. So we're going a different direction now. So let's see. Let me erase this for you. Okay. So the next problem I had was going from, I wrote 8.38. I can as far back this way as I can. Times 10 to the 23rd molecules of, what did I use? N2O5. And I want to go from molecules to grams. So molecules to grams, which means molecules is right here. Here's my unit for molecules. And I need to go to grams right there, which means I need to find the molar mass again. So right away, if molecules is what I'm starting with, I know in the bottom I'm going to need molecules. Molecules is here, which means my number is 6.02 times 10 to the 23rd. So I'm going to write that right there. They call that Avogadro's number. Okay. And then my molecules will cancel out, but I need to know what to put on top. So I just use my triangle. 6.2 times 10 to the 23rd molecules goes on bottom, so my units cancel. I'm trying to get to grams. So grams is right here. I need to find the molar mass. So my molar mass, Okay, so it's nitrogen, which I have 2 of, times 14.0 equals 28.0. Oxygen, I have 5 of, times oxygen 16. 16 times 5 is 80. That's going to give me 108.0 grams. So I'm going to write that right here. And then I'm just going to calculate it. And when I calculate this, I'm going to plug this in the calculator. Something you want to be careful about is that you plug this in and you use parentheses around here. What happens to a lot of people is they'll plug this in a problem just like this. They'll plug 8.3 times 10 to the 23rd. They'll write times 108. Then they'll put divided by. They won't use parentheses. And they'll do divided by 6.02. And they'll write in 6.02 times 10 to the 23rd. And what your calculator does is it does this number times this number, divides by your 6.02, and it'll calculate for you and take that whole thing to 10 to the 23rd, and you'll end up with a mass of like 10 to the 46. And that clearly is wrong because you're not going to have a mass that high. So instead of dividing by the 10 to the 23rd, it tries to multiply it by it because you didn't use parentheses. So you have to be careful that you use parentheses, and because your calculator tries to outsmart you and it thinks it's doing orders of operations and whatnot, and it'll mess you up. So you have to plug this in correctly. So parentheses, 8.38 times 10 to the 23rd, close your parentheses, times 108, and divided by parentheses 6.02 times 10 to the 23rd, close your parentheses. If you do that correctly for this particular problem, you would end up getting right at 150. Okay, this is tricky because it came out to like 150.3 or something like that when I calculated it. Can't remember that's exactly what it was, but it's something like that. But you have to have 3 significant figures because this is my lowest right here. So if this, I can't write 150.3 because that would give me 4 significant figures. I can't leave this as 150 because this would only be 2 significant figures. So when I write my answer, what I'm going to do is I'm going to put a decimal point right here to tell me that that 0 is significant. Now I have 3 significant figures. And then I'm going to write my unit, grams N2O5. And that's my answer. All right. Units canceled, units checked out, everything is good. I use the proper conversion factor using my triangle, and I'm good to go. All right, I'll do one more example for you guys, and then I'm going to call it a night. Okay, so in this next example, I wanted to show you guys something just with our formula writing. So I chose calcium acetate. So calcium acetate this time. So I chose 0.76 moles of calcium acetate. So calcium is Ca and it's a 2 positive. Acetate, if you look at the periodic table, on the backside, you're going to find acetate up here, and it's this long one, CH3COO. CH3COO. Now, what you'll see, and I'm sure I have it on a few worksheets this way, is that CH3COO 1 negative can be written a different way. So you will see this. I know I have this on a few worksheets, where instead of writing CH3COO, which they write because the structure of this particular ion happens to do that, but what a lot of times what we do is we just say, okay, well, why write C twice? Instead, let's just write C2H3O2, and it's still 1 negative. So both of these are saying the same thing. This just tries to show you the structure of the molecule, which we personally don't really care about right now. We're more just worried about what we have and that it's this ion with this charge. So in this case, in order to write this out, I have a 2 positive. I still need both of these. So 1 negative, 1 negative, which means I need 2 acetates. So when I write my formula, I'm going to write Ca, and then I need 2 acetates. I'm going to write it the second way, C2H3O2. I could have wrote it the first way. It really didn't matter, but I need 2 of them. Okay, so I'm good to go. Now I'm going to go from moles. I think I wanted to go to grams if I'm not mistaken. Yeah, I decided I was going to go from moles to grams. So in this case, moles here. Okay, so I need mole to cancel out, which means I need to put my 1 mole right here. 1 mole of Ca C2H3O2, 2, and I need to figure out my molar mass. So I got to go through this whole mess again. So again, calcium when you get used to doing molar masses, you probably won't have to write these out every single time. Sometimes you just get good at just plugging in the calculator. I personally don't mind which way you do it as long as you get them right. So I just write this out because I'm still showing you guys how to do this. So in this case, calcium, I have one of them times 40.1, which of course is 40.1. Carbon, I have two of them times 2, so I end up with 4 carbons. So 4 carbons times 12.0 equals 48.0. Hydrogens, I actually have 3 times 2. I have 6 hydrogens. Luckily, that's just times 1.0. And then I have 4 oxygens, which is 4 times 16, which gives me a total of 64. And if I add that all up, I end up with 158.1. Hopefully I did that right. And then, of course, my moles cancel out. My units check out. I got this from using here because 1 mole is equal to molar mass. 1 mole is equal to molar mass. So I set that equal to each other. And then I just went through and I calculated it. When I calculated this one, I only needed 2 significant figures. Again, be careful with that. 2 significant figures here. So it came out to, whatever it came out to, I had to round. So I ended up with, I'm just going to write it down here so I can reach, 120 grams Ca C2H3O2. So 120 grams of calcium acetate. So that's 3 examples of just making mole conversions. I would recommend using this triangle. Just get used to it. Mole conversions, you've got to be able to like perfect. You've got to get really good at it, especially for what we have coming down the road. You will make mole to grams and grams to moles conversions so often that's got to be second nature. Especially as we get into these next concepts, and especially when you get to the next unit, you make that conversion so often. Not this one so much, and not this one so much. Comes up every so often, but this one here, going from moles to grams, grams to moles, you have to be able to do that, like almost like second nature. So just practice it. If you have questions, feel free to ask me. Just shoot me an email, ask me on Teams, whatever. If there's specific problems you want me to work out on the worksheets, just tell me which ones, and I'll post them in that notes section. You'll see a bunch of examples I did on there too, but I can do whatever problems you guys want me to do. Just let me know, just communicate with me, and I can do whatever you guys need me to do. So hope you guys are doing okay. Miss you guys. It's really tough teaching at home. I'd much rather be in the classroom doing this. So you guys take care, and I will see you online soon. Bye bye.